Alright guys, let's take a look at today's lesson. What we're going to do today is we're going to combine U-substitution with definite integration. Now, if you can actually do your definite integration with U-substitution like we've done U-sub before, so let's talk about that. We learned how to do definite integration yesterday, where with the fundamental theorem of calculus, we would find the antiderivative, do f of b minus f of a. You can certainly do that. You can do your U-sub, you can put the U back in, and you can do it just like we did yesterday. That is certainly possible. And some students actually prefer that. But this technique that I'm going to teach you today is really important that you understand whether you use it as your primary technique or not. There are questions, I have seen questions on the AP test that require you to know how to do this change of bounds. I'm going to teach you today how to do U substitution, leave the U in, and change the bounds. Okay, so again, really important that you understand how to do it, because I've seen questions in abstract, without an equation, where you wouldn't have a choice on what to do. You would have to understand how to change the bounds. So that's going to be pretty important for you. So let's go through and talk about how that works. In order to do this, of course, the U substitution is just, we have to have a function and its derivative embedded inside the integrand. We've worked with U substitution before. These are x's and dx, and these are x bounds. The a and the b belong to x. They are x bounds. What we're going to look at today is going ahead and completing the U substitution and taking the x bounds, and instead of them being x bounds, changing them to U bounds. That's our goal for today. So let's do that. Let's start with the first example. On this one, we would let u equal 3 minus 5x. So du would be negative 5 dx. Now I don't have a negative 5, so I'd move it over. Negative 1/5 du equals dx. At this point, what I do every time is I immediately change my bounds. Immediately. The way that I do that is I take the expression that I set up for u and I substitute these x bounds inside of it. So this is at x of 1, so I would change it and I would do 3 minus 5 times 1, and that's going to be a negative 2. So my new u bound at that location would be a negative 2. Then I take the next one, so 3 minus 5 times 2. And that would be 3 minus 10, or negative 7. Now, I write that down because I have issues with arithmetic, and sometimes I need to go back and check my arithmetic. I don't care if you write that down or not. You can do it in your head. It's totally up to you. But for me, I like to have a trail of what I've done so I can go back and check my work in case it turns out bad. All right, so we're going to go ahead and change our bounds. Now, I do want to mention one thing about this, and we haven't talked about this with integration very much. We have taken it for granted that the function is going to be continuous on the interval. We've been taking that for granted, okay? And most of the time, it will turn out well for us. But there will be an occasion, and perhaps on the AP test, where it's not continuous on the interval. So in this particular case, which number would cause this to be discontinuous, would cause this integrand to be discontinuous? 3/5. Now, luckily, 3/5 is not in the interval, so it's not a problem for us. But that is something that we really should be looking at and paying attention to, making sure that it is continuous on the interval, because that's a requirement to do this technique, to do the fundamental theorem of calculus, is that it's continuous on the interval. So just keep that in mind as you work these problems. All right, so let's go ahead and change our bounds. Let's see, that became a negative 2 and a negative 7. Now there are some of you that are going to be really upset that they're not in order. Please don't let that bother you. It's okay. It doesn't have to go from little to big. It's all right to be negative 2 to negative 7. So don't let that disturb you. Now we finish up. We took out the dx, and we're going to put in a negative 1/5 du, and then we took that out, and that was u squared. All right, I'm going to just rewrite it. So I have negative 1/5 integral from negative 2 to negative 7 of u to the negative 2 du. All right. Now, I am completely done with the x's. I'm never going back to them. I'm not going to be working with them anymore. My equation now is simply in u's, and I'm going to keep it there. I like this technique because what I end up integrating and using my arithmetic with is typically an easier an expression rather than putting this back in and going through that. So for me, I like this technique, and that's what I would be doing. All right, so let's go ahead and work that. So I add 1 to negative 2, and I get negative 1. So I had a negative 1/5 out there, and that would be a negative 1 over u to the first, evaluated from negative 2 to negative 7. So probably what I would do here is, you have choices. You can, and I've been asked this question, it's a personal preference. It's not a rule. I can go ahead and distribute the negative 1/5 inside here if I want to, or I can leave it out. It's up to you. Whatever you think is easier. Doesn't really matter. I'll do one way and one another, so let's leave it out this time. So that gives us negative 1/5. Okay, so we're going to substitute the negative 7 in. So I have negative 1 over negative 7 minus, then I have negative 1 over negative 2. And that's an awful lot of negatives that we could easily get confused with. Hopefully we don't. I'm not going to go through the arithmetic part. Leave that to you. And just know that my final answer would be 1 over 14th. Okay, so how's our very first u substitution with a definite integral? Is it okay? All right, and let's, I normally put this part in a little bracket just to keep it away from the rest of the work, just so that I know I can follow my own work, what I was doing up here. All right, let's look at our next one. So here, we're going to make u equals 1 plus 2x squared. So our du is going to be 4x dx. I don't have a 4 in here, so I'm going to move the 4 over. 1/4 du equals x dx. I'm going to immediately change my bounds. While I'm in the u sub thing, I'm just going to go ahead and just finish it out. So u is going to be 1 plus 2 times, my lower bound is 0, so that turns to 1. Or 1 plus 2 times 2 squared. Let's see, that'd be 4. 4 times 2 is 8, so that's 9. So those are my new u bounds. And that's my u sub work. All right, so we're going to change the bounds. I'm going to go from 1 to 9. The x dx is gone. I have a 1/4 du in its place. And then I have u to the 1/2. Okay, we okay? And so if you want to rewrite that to be u to the negative 1/2, you can. I'm not going to do that this time. But if that makes you more comfortable, go ahead and rewrite it to make u to the negative 1/2, so you can see that it's a reversal power rule. We want to add 1 to the negative 1/2 and get what? Add 1 to the negative 1/2 and get 1/2, and then divide by 1/2, which is multiplying by 2. And that would be u to the 1/2 from 1 to 9. Now here, just for fun, let's just go ahead and multiply that out, rewrite it. That's going to give me 1/2 u to the 1/2 evaluated from 1 to 9. So here I'm going ahead, I'm multiplying that in. Here I left it out. It's just your choice, doesn't really matter. So I have 1/2, and then we have what, square root of 9 minus square root of 1, or 1/2 times 3 minus 1, which is what? 1. Okay, so that's our second u substitution, changing the bounds. Okay, getting a little more comfortable. Okay, we have a few more examples. Does anybody still need this? Sure. So the other way, again, the other way would be to put the u back in and keep everything x and use your x bounds, and you can do it that way too. There's nothing wrong with that. You just really have to know how to do this. All right, let's go to our next slide. Okay, let's take a look at this one. So here, I'm going to do a little baby U substitution. I would like eventually, and most of you will be able to do this U substitution in your head eventually. I'm not going to do that with you yet, but eventually you should be able to do this in your head. So du equals 3 dx, 1/3 du equals dx. Go ahead and change my bounds. So u is going to be 3 times pi over 12, which is what, pi over 4. And u is going to be 3 times pi over 9, which is pi over 3. So there's my u sub work. Okay, so now let's transform our integral into all u's. So let's see, I've got a 1/3 out here, and my bounds go from pi over 4 to pi over 3. Okay, so if we had taken the derivative of something and had gotten a positive sign, so this would be sine u du. If we had done that, what would we have taken the derivative of? A negative cosine. So I have 1/3 times negative cosine u evaluated from pi over 4 to pi over 3. Okay, so that's negative 1/3 cosine of pi over 3 minus cosine of pi over 4. Is everybody okay? Now, for those of you that love trig, like me, and have your unit circle memorized, this is a fantastic problem for you. If you don't have it memorized, please do, because it's never going away. Okay? Never. We're going to be working with trig all year long. Just little pockets here and there. Okay, so unit circle. Cosine of pi over 3, that's this one up here, would be 1/2. So 1/2. And pi over 4 would be that 45-degree right there, which would be root 2 over 2. Now, since we are a bunch of little fractions, you can leave it like this. I encourage you to just distribute the negative 1/3, and then you can stop. Or you can get it into one fraction, just whichever. Where this is going to make a big difference is on multiple choice problems on the AP test. That's where it'll make a big difference, because this is the correct answer, but they probably aren't going to write it that way. And perhaps they may even write it combined as one big thing. So negative 1 plus root 2 over 6. You just need to be able to recognize that. Okay, just recognize that. Get it in simplest form for me. This would be considered simplest form, or like you can add them together. Sure, yeah, you can add them together and make one big fraction. Either one of those is considered simplest form. Okay, so we okay with that? All right, next one. Hopefully you're comfortable enough with u sub to know exactly what to make u here. Sine, right, because it's cubed, right? Sine x. Du equals, so your derivative of sine is cosine x. So we don't, dx, we don't have any constants to mess with. So let's go ahead and go into our change of bounds. So u is going to be sine of 0, which is 0. And u is going to be sine of pi over 6, which is 1/2. So what's kind of nice about this, in this case, we've already done all the trig we're going to do in this problem. There isn't any more trig to do, because when we rewrite it, we have our new bounds from 0 to 1/2, and this part was gone with our derivative, and this turns into u cubed, and basically I don't have a trig problem anymore. Okay, I don't have a trig problem anymore, which is kind of sad because I love trig, but we will deal with it. So we get what, 1/4 u to the 4th from 0 to 1/2. And then so 1/4 times 1/2 to the 4th minus 0 to the 4th. equals 1/4. What? 2 times 2 is 4. 8. 16 times 1/16, which is 1/64. Okay? And there is our fourth one. Okay? All right, great. Our last one, we're asked to find the area bound by that graph. And they draw it for us, which is nice, and the x-axis and the interval 0 to 2. All right, so this is what we're looking for. So we're going to integrate from 0 to 2 for x square root of x squared plus 1 dx. That's the integral that we're going to do. So let's do our u sub. U is going to be x squared plus 1. Du is 2x dx. I have a constant to deal with, so let's move it over. Let's go ahead and change our bounds. U equals 0 squared plus 1, or 1. And u equals 2 squared plus 1, or 5. So I have the integral from 0 to 5. Got a 1/2 here. And then, oh yeah, 1. There we go, 1 to 5. Got a 1/2 there, and we have what, u to the 1/2 du. All right, so let's integrate. So 1/2 plus 1 is 3/2, so we multiply by 2/3 u to the 3/2, evaluated from 1 to 5. I would probably, just for simplicity's sake, go ahead and multiply these together, and I would get 1/3 u to the 3/2 from 1 to 5. All right, so let's do that. 1/3. We have 5 to the 3/2 minus 1 to the 3/2. Now, since it was given in radical form, the answer would probably be in radical form. This would most likely be a multiple choice problem, and so we really need to convert it back to radical form. So the square root of 5, we need 3 of them. We need 3 square roots of 5, which would be that, right? You're okay with that's 3 square roots of 5. 5 root 5 is 3 square roots of 5 minus 1. And they may leave it like that, or they may distribute the 1/3. Most likely they would probably leave it like that because it's prettier than distributing the 1/3, but either would be fine. And let me point out, if you did this in your calculator to check, it probably would come out with a slightly different answer than this. Because your calculator is using an approximation program to calculate the integral, it's when we have radicals or cube roots or something in it, it many times isn't right on. It's usually wrong out about the 5th or 6th decimal place, 4, 5, 6, somewhere in there. It's wrong. So if you check your work with your calculator and you put this in and get a decimal, and then you put this in and get your answer, please don't be alarmed if it's different way out in the 4th or 5th decimal place. Okay, because that's just what your calculator does. It just approximates. Okay? We okay with this lesson?